Okay, the purpose of this screencast is to discuss integration. It's a supplement to the notes where it's explained in great detail. And let me just tell you what the main goal is. So the main goal is to upgrade the existing notion of integration on Rn, to integration on a general manifold. Okay, and the basic idea, okay, is that a function f, which is a zero form on M, should be thought of as a function on points. In other words, you can evaluate a function on a point of the manifold and get a number. But k-form, rho, you should think of this as a generalized function. It's a function on k-dimensional submanifolds. So what we're going to see is that if you take a k-form on the manifold M, and if you have a k-dimensional submanifold, then what you could do is take this form, pull it back to the k-dimensional submanifold, and integrate it and get a number. So that means that a k-form, you could think of it as a function, but it's not a function of a point, it's a function of an entire k-dimensional submanifold inside the manifold. The only thing is that we are going to need this submanifold to be compact, and we're going to need it to be oriented. Instead of compactness, you could assume that the form has compact support, which is what I do in the notes. Okay, but for now, let's just... in any case, the most important thing is that the submanifold must be oriented, and the differential form must be of compact support. So in other words, I could remove this compactness and say oriented, and then I'd have to put here a C, which means that it's compact support. Yeah, compact support, K-form. All right, so let's begin with the basic ingredient. Which is that, which is the change of variables formula for integration on Rn. So suppose we have Rn with coordinates x1 up to xn, and suppose we have other coordinates y1 up to yn, and suppose we have a diffeomorphism between Rn and Rn. So this is a change of variables from the x's to the y's. Okay, and suppose that we have some function which is of compact support on Rn. I'll denote that by putting a little c. So compact support means that there's a compact set where the function is 0 outside that compact set. So all the interesting stuff about the function, the values, they all take place in a compact set inside Rn, a closed and bounded set inside Rn. Okay, so given this function, we can integrate it, and we produce the integral of f dy1 dyn. It's an integral over Rn, and we get a real number. Okay, so if we change the variables, then what we see is that this quantity is equal to the this is the function, this is the pullback function. So now I'm taking this function of y, and I'm just substituting the variables x in them. So I'm composing f with the change of variables. So now this is the pullback of f, and then I'm going to integrate in the dx's now, still over Rn. But now the point is that I need to include the Jacobian determinant, which is, usually you'd write it like this, d by d yi d by dx j, and then you'd take this matrix and take the determinant of that matrix. So I'll put the determinant like this. Well, sorry, I'll put determinant like this. Okay, so the determinant of the Jacobian matrix, and then you'd need also to put the absolute value of this. This is the formula for change of variables. This is the basic ingredient. Okay. So just to emphasize, if I have a function on Rn which is positive everywhere where it's non-zero, right? So let's say that it's like a bump function which has positive values inside a compact set. If I integrate that function in one set of variables, I'm going to get a positive real number out of it. Similarly, no matter how I change the variables, I'm always going to get a positive integral for that function. That's the reason why, well, that's one way you can see that there must be an absolute value here, because you may do a change of variables such that this determinant has a negative value, but the integral of that positive function, you always want it to be positive. So in the traditional sense of the Lebesgue integral, when you change variables, you always have to put the absolute value of the Jacobian determinant here. Okay. All right. So the major observation now. So how do we upgrade to general manifold? Okay. The way that we upgrade this is to just observe that this Jacobian determinant, we've seen it before in the change of variables formula for differential forms. We know that dy, let's say dyi, say, is the sum of dyi dxj dxj. So this is just the pullback formula. So this is, technically speaking, what this is. So I'll just put this in quotes, just because this is slightly imprecise. What's more precise is that phi pullback of dyi is equal to the sum from j1 to n dyi dxj dxj. Okay. So okay, and now so now we have the Jacobian, but we need this determinant. Well, so the observation is the following: that if I take the wedge product of these, so if I take dy1 wedge dy2 wedge all the way up to dyn, so this is a generator for the highest exterior power before the exterior powers become zero. So this is the top power, and if we take the pullback of this whole thing, then what we're going to get is a wedge product of all of these expressions, right? So I'm going to have dy1 dxi1 dxi1 sum over i1 wedge the same thing i2 dy2 dxi2 dxi2 wedge all the way up to the top degree, which is dy. It'll be a sum over in of dyn over dxin. Okay, and so then we need to expand out this wedge product. But as you can see, so this is a wedge product of n elements. But the top exterior power, so this has to be a single number multiplied by the single generator, dx1 wedge dx2. There's only one generator for this nth power, because I only have n coordinates. So there has to be a single number here. And what you see is that this number is exactly the Jacobian determinant. So this is determinant of dy I over dxj. If you just sum up all the terms, this is a general fact about the exterior algebra, that if we have a matrix this is the general important fact about the exterior algebra. If we have a matrix, an n by n matrix, and if we let the rows, or you could do this with the columns too, but if you use the rows to build n different vectors, second row 2 1, if you take the wedge product of all the rows, what you get is exactly the determinant of the matrix. Times the basis element. Okay, and and so what this is telling us is that almost everything about this formula is explained by the change of variables formula for the n forms, or in other words, the pullback formula for the n forms. So, so in other words, what we could say is that this formula, let's give it a name, star may be rewritten that the integral of over Rn of f, so it may be rewritten as follows. Okay, we could say that we can say that let rho be a differential form, which is f times dy1 wedge dy n. Okay, so inspired by this thing, what we'll do is we'll think that what's being integrated here is not f, but actually a differential form, which is f dy1 wedge up to wedge dyn. Okay, so we'll interpret the left-hand side of that equation. So the left-hand side, we'll interpret it as the integral of rho on Rn, where rho is given by this. Okay, and the right-hand side is that it's the integral of the pullback of rho. Okay, so we'll, in other words, we're going to assume, we're going to interpret this equation as saying that that actually this is a n form, and we are integrating it, and the result is exactly this number which you know from advanced calculus. And on the other side, we have another form which is being integrated. But what is the form? The form is actually the pullback of this form. Okay. Now, what's the problem with this? So this is so the problem with this is that this takes into account all of what's happening here on the right-hand side, except for the fact that we have an absolute value. Okay. So this is consistent with star, okay, if one, we just define the integral of rho locally, so of this rho, right? So if we take an n form, and any n form can be written like this. Yeah, let me write it this way. Define the integral of rho, which is an element of omega n, of an n-dimensional manifold. So we'll assume that M is an n-dimensional. We'll define the integral to be locally given by. So if we take rho and write it in local coordinates as f dy1 dyn, if the coordinates are, let's say, y1 up to yn, then we'll say that the integral of rho is the usual integral of f dy1 dyn. So this is now not a differential form, but this is just the Lebesgue integral, or the usual Riemann integral of a smooth function in n variables. Okay. So if we define this integral in this way, then this is consistent with the change of variables formula, as long as we only use changes of variables such that the Jacobian determinant is positive. It's positive. Okay, so the conclusion is that we can define an integral on manifolds for an n form by doing the following. We say, choose a coordinate system locally, write the form, the n form. I'm not doing a k form. I'm only going to do an integral for n forms. And what I'll do is take my n form, write it locally in this way as a function multiplied by this generator, and I'm putting the coordinates in order, dy1 up to dyn. Okay, so write it this way, and then we'll define the integral to be just the usual Euclidean, usual Riemann integral. Okay, and this will be this number, the result, okay, will be independent of which coordinate I chose, as long as I only allow myself to change coordinates in such a way that the Jacobian determinant is positive. Because then, when I look at how this thing varies with a change of coordinate, this formula is going to tell me that that this absolute value is unnecessary, all right? And so this star formula will not have these absolute value signs, and we'll just get exactly the behavior of this form. Okay? So in other words, it won't depend on which coordinate system I use to write the form in. Okay, so but this is strange because what this means is that in order to compute the integral, I would have to. So what does this mean? This means that to compute a global integral, an integral over all of M of a form, I would need an atlas okay, such that the gluing maps phi ji, which is phi I inverse composed with phi j, okay, that these things have positive Jacobian determinant. Okay, and this is one way of defining what it means to have an orientation on the manifold. Okay. So this is one way of thinking about what an orientation is. If the manifold is oriented, it means that that charts, some charts are good and some charts are bad, in the sense that they're either charts that have positive comparison to this nice atlas, or negative. If the chart compares with the atlas to be negative, then we exclude it. Okay, so here's, but notice that if we have two charts, like notice that if we have so let me just put a comment. So notice that if phi ji has negative determinant, negative Jacobian determinant, right? Then what you could do is take one of the charts, right, and just replace it with a map. So what you do is take this chart, one of them, let's say, phi I, and replace it by another chart. Let me just make this a little nicer. So this is phi I. So we're going to define a slightly modified chart. I'll call it phi I tilde, which takes the coordinates and just flips the sign of one of these coordinates. Doesn't matter which one. Okay, so this, because of this fact, right? If I compute the Jacobian determinant, the Jacobian of this map, this modification map, it just the Jacobian just looks like -1, 1, 1, all the way to 1, right? So the determinant of this part is -1. So in other words, if this thing had negative Jacobian determinant, then phi j, phi tilde I inverse will have positive. Okay, so in other words, if if you want to use, so if you have an orientation, namely if you have a choice of atlas such that the gluing maps are positive, and if you have some other chart that you're interested in, and maybe it compares badly with the atlas, maybe it doesn't have the right orientation, then what you could do is modify it just by post-composing it by one of these maps. That's just a comment about how easy it is to change the orientation of a given chart. Okay, but there's another way of thinking about orientation, which might be well, some of you might prefer it to this notion of orientation. So another way of defining the orientation is like this. So if V is a real vector space, let's say n-dimensional vector space, then this implies that the nth exterior power of V is one-dimensional. Okay, and we define an equivalence relation. Let's say V1 is equivalent to V2 when there exists a positive real number with V1 equals lambda V2. Actually, there's an equivalence relation on non-zero n form, n vector, well, non-zero elements of the top power of V. Okay, so we'll say that if I take V1 and V2, elements of wedge NV, which are non-zero, then we'll say that V1 is equivalent to V2 when there exists a non-zero lambda such that lambda V1 is equal to V2. So in other words, the top exterior power, this is the thing that I keep calling the top exterior power. And some people might call it the determinant of V. It's not the determinant of a map, but the determinant of a space. Okay. Then you could draw it like this. You could say that this is the determinant of V, the top power of V. And I'll just indicate that V1 and V2, okay, they are equivalent because you can just multiply V1 by 2 and you'll get from V1 to V2, right? Similarly, this V1 and this V2 are equivalent. Okay, but you cannot have two vectors on either side of 0 being equivalent, because they must be positive scale multiples of each other. Okay, so so that's the first thing. So the first part of the definition is that there's an equivalence relation where two non-zero elements of the determinant of V are equivalent when they're related by a positive scalar multiple. And the second part of the definition is that an orientation on V is a choice of equivalence class. Okay. So sometimes what people will say is, I should say, okay, so here's a bunch of remarks. So remarks. So first of all, if we have an ordered basis usually when I define a basis for a vector space, I always let it be ordered. Okay, I mean, but some people define a basis to be not necessarily ordered. So if we have an ordered basis, E1, En of V, then we have a natural orientation, which is to take the ordered wedge product of this ordered basis. You take the wedge product of the ordered basis in the order given. And this gives a non-zero element of the top exterior power, and we take the equivalence class of this. Okay. So this is like yeah, all right. So this is giving us a natural orientation. So this means that Rn has a natural orientation, has this natural orientation. And I should say, like, there are only two orientations, right? There's this one, the one on this side, and the one on this side. There's only two possible choices of orientation, that's all. But it's important which one you pick, because it all differs by a sign, and that will affect the integral. Okay. Okay, so now, what was the other remark that I wanted to make? Sometimes, second remark is that in R2, for example, for a two-dimensional vector space, here's a two-dimensional vector space, oftentimes people say that an orientation is given by an arrow that's like this, like a rotation direction. Right? They say this is one orientation and this is another orientation. Okay, and this is very much related to the first remark, because if I wanted to represent this arrow, this rotation direction as an orientation, what I would do is I would pick a non-zero vector, E1, and then rotate it in this direction, any amount, it doesn't really matter, to get my second basis element, and then I would use this ordered basis to produce the orientation given here. So I would have E1 wedge E2, and then I'd have the equivalence class of that generator for the top exterior power. On the other hand, here, if I choose my same E1, or whatever I choose, the second vector will be, so if I just rotate it a small amount, then I'll get E2 like this. And then I'll use the same convention. And then I'll get a different orientation. So as long as, you see, as long as you only rotate a small amount, if you continue rotating, if you start with E1, right, and you start rotating in this direction, you're allowed to use E2, but then at some point, this thing is going to get closer and closer to minus E1. And as soon as it gets to minus E1, then the wedge product of this with this, E1 wedge minus E1, this is equal to 0. And so that means that you've passed, when you pass 180 degrees, you pass from one orientation to the other. So the meaning, if you wish, the interpretation of this rotation direction as giving you an orientation is to say that you should pick any vector and then just rotate it a small amount, and then just take E wedge F like this. Okay? I'm just trying to explain why it is that when people sometimes give you an orientation, what they do is they draw a little arrow that indicates how you should rotate in a way that produces the right orientation. Okay. Anyway, like we said in class, right? Anytime that you do something for vector spaces, you could do it for vector bundles. So let's continue the definition. So an orientation on the vector bundle V over M is a smooth, well, I can say it like this, is an equivalence class of nowhere vanishing n forms. Let's say this has rank k. So that means it's a smooth family of k-dimensional, let's say it's rank n vector bundle. That, what I'm saying is I'm not talking about the dimension of M, I'm talking about the rank of V. Okay, so V is a family of n dimensional vector spaces. And so I need to take a smooth section of wedge n, let's say over the manifold M, of wedge n of V. Okay. Where of course V1 is equivalent to V2 if there exists a nowhere vanishing, a positive function such that V1 is equal to F V2. So this is just a smooth version of the vector space definition that we had before. And in particular, an orientation on M, on the manifold M, okay, is an orientation for the tangent bundle of M, which is a vector bundle over M. So when we say that a manifold is oriented, what we mean is that the tangent bundle is oriented as a vector bundle, which means that we have to choose a nowhere vanishing section up to equivalence of the top power of Tm. Actually, it makes no difference whether we use Tm or T star m for this purpose. And so oftentimes we'll just use the cotangent bundle. So this means that an orientation is specified on M by a class of n forms where V is nowhere vanishing, okay, and and such an n form on the n-dimensional manifold M is called a volume form. Okay. All right, so I just wanted to, these are two notions of orientation, right? One of them says that the manifold has an atlas where the gluing maps all have positive comparison, positive determinant of the Jacobian of the comparison map. Okay, and the other says that it has a nowhere vanishing n form. Okay, and the relation between the two is that, so what's the relation between these two definitions? So definitions are equivalent, okay, because if we have an oriented atlas, if the atlas is oriented, then what we could do is just we could just take a partition of unity adapted to the atlas, let's say Fi, right? And then we could take in each chart, we could just take the standard volume form. This is a volume form, right? And we could just, so this is for the ith coordinate. Let's say that I'll just put an I to indicate that it's the ith coordinate chart, and then just scale it by Fi, right? And then we could take the sum over the index set for the chart. Okay. And this thing is what I'll call V. And so this will be a nowhere vanishing rank n form. Okay, so that's in one direction. On the other hand, if V is a nowhere vanishing, is a volume form, and you give me some atlas which may not have the good property, the oriented property, and if this is any atlas, then for each I, we could modify the chart, if the chart phi I, if dx, if the standard volume form dx1 up to dxn, if this thing here is not equivalent to V, if it's equivalent to minus V instead, right? That means then what we could do is modify the chart to phi I tilde. If the chart is such that the standard volume form is equivalent to V, then we don't need to do anything to it. So you just scan through the atlas and you flip the coordinates of those charts which disagree with V. Okay, so that's showing you that these two definitions are really the same idea. Okay. But as a result of this notion of orientation, there's a theorem, which is 6.16 in the notes, which says that if M is oriented n manifold, okay, then there is a unique linear map. The integration map. And what does it do? It takes an n form on M and produces a number. We only need that the n form has compact support in order to have a finite integral. Okay? And when we say that it's unique under the following assumptions. With the property that if H is orientation preserving, diffeomorphism basically this is like the inverse of a chart. If it's an orientation preserving diffeomorphism from an open in Rn to an open in M, and if we have a form with support contained inside U, then the integral is just given by the integral on Rn. So again, this is basically saying that if we okay, you can look at the notes for the proof, but the whole discussion that I just went through is really the proof of this theorem, more or less. So what I mean is that this theorem is saying that if you use the usual integral in Rn as our local definition for the integral, then it automatically globalizes to the whole manifold, as long as we understand that what we're really integrating is not a function but an n form. Okay. The only thing that's remaining is to make precise how we go exactly from this local computation to the global one, and that's going to be through a partition of unity. So in other words, so the basic proof is going to be that if we want to integrate if we take, let's say, an n form on M, then we want to integrate it over M. So what we can do is choose a partition of unity. In the notes I call it theta I, partition of unity. Okay, so so this is just a sum of theta I alpha because of the fact that it's linear. The linearity of the integral is allowing us to split this into a sum. And then what's great about this sum is that now this thing has support inside a small open set of a chart. Let's say this is a partition of unity adapted to an atlas. Okay. Then this thing will be I'll have an atlas, let's say ui, and then phi to vi inside Rn, right? So this means that what I could do is take phi I inverse and pull back this theta I alpha. So this is phi I inverse, right? I take the form theta I alpha, which is supported in ui. I pull it back under this. That's in vi. And in vi, it's exactly just the integral that we know. So it's the integral on Rn of this pullback. So this is an integral on Rn. Okay, so what this means is that we have a proposal just by using the definition, or sorry, just by using the properties that are required by the theorem, we have an expression for the integral itself. In other words, we have a candidate just based on the properties required. By linearity and by this local equivalence with the standard integral, we have an ability to calculate any integral of any form given by this expression. Okay? All we need to do now is to verify that this particular expression satisfies these conditions, the conditions of the theorem. So in other words, uniqueness follows from just this argument. This is the unique possible map. The only question is whether this map satisfies this condition for any orientation-preserving diffeomorphism, and for this we need to use the change of variables formula, like we discussed. Okay, so that concludes the motivation and definition of the integral. And so, you know, the way that we will use this typically, right, is that we'll say that you know, if I have an n-dimensional manifold, right, and if it's oriented, okay. So for example, S2 is oriented, or T2, or S1, you know, all the spheres are oriented, products of oriented manifolds are oriented. If you take the genus G surface is oriented. Which other manifolds did we see? All complex manifolds are oriented, so the CPNs and the Grassmannians for complex Grassmannians, these are all oriented, etc. And so RP2 is not oriented, is not orientable, meaning that you cannot choose an orientation, but RP3 is. In fact, all even projective spaces are not orientable, whereas the odd ones are. And okay, and so what we'll do is say that if I now have an n form with compact support, then I can integrate the n form and get a number. But keep in mind, so that's one way to use it, but keep in mind also that if I have a submanifold, an oriented submanifold of dimension k, and if V is now a k form on M, I cannot integrate V on M because V has to have degree n to integrate it over M. However, what I could do is look at the inclusion map of L into M, and I could pull back V by the inclusion map, and this now will be a k form on L, which is now a top degree form on L. And so that means that I can integrate over L I star V. So we see, as I explained in the goal at the beginning of this, having a k form you may not be able to integrate it over all of M, and you may not be able to evaluate it at a point and get a number. But if you have an oriented submanifold of dimension k, then you could take this k form and integrate it over L, and we would get a number. So it is indeed a function on k-dimensional submanifolds. So in the next screencast, I want to describe Stokes's theorem. Stokes's theorem is basically describing the behavior of this function as you change this submanifold. I'll explain what I mean in that video.